All right, so the last part of this chapter is all about amides and nitriles. They're the least reactive of the carboxylic acid derivatives. And so let's take a look at some simple reactions that we've seen already, and we'll start off with preparation of amides. We saw this previously, that you can convert an acid halide to an amide by using some sort of amine. So in this one, I'm just going to use ammonia in excess. And I'm going to convert the acid halide into an amide. There's a bunch of other ways to make amides that we'll talk about later in the term, but for right now, this is the primary way that they show. Like I said, you can do this with anhydrides, but it really works best with acid halides. Anhydrides tend to be a little bit slower. I'll show you an example reaction of this that's actually a commercial reaction. Take this diamine. You can react it with an acid halide. And what do you think happens if you react these two together? You're going to make an amide. But what type? Think it's going to stop after one unit clicking together? Oh, you got two sticky ends. So in reality, what this will do is form a big long polymer. One of my favorite polymers. Slide this over a smidge. And I'm going to put brackets around this because theoretically this can repeat many, many, many times. Does anybody know what this polymer is called by chance? Some of you that served in the military probably wore this as protective coating. Kevlar. The reason that Kevlar is such a good bulletproof material is these bonds are really, really, really strong. In fact, Kevlar is used in the International Space Station too. They wrap the space station in Kevlar because it's lightweight. And if there's any micro debris, it can actually catch some of that and prevent catastrophic damage to space equipment. So Kevlar is a really cool polymer material because it's very, very strong and it's very, very light. One of the big problems they had with the first generation of bulletproof materials was it was quite literally made of steel. Soldiers don't like wearing steel because it's very uncomfortable, it's heavy. They would take off those steel plates and expose themselves. So this is much, much safer for everybody. All right, so let's take a look at some reactions of amides. I think one of the coolest videos is, I don't have it on here, I should post it though, is with Kevlar. It only takes, I think, like 8 sheets of Kevlar to stop a 44 Magnum. It's unbelievable how strong it is. The problem with it is the kinetic velocity of those bullets. So powerful, it'll break all your ribs and potentially cause internal bleeding. So it'll stop the bullet from going through you, but it'll still really, really hurt. Okay, so let's look at acid hydrolysis. This is one we actually saw in our pod a while ago, if you remember. Where in the pod, we took a nitrile, and under acidic conditions, it actually converted to an amide. However, if you heat it with enough acid, you can actually blow past the amide and convert this all the way to a carboxylic acid and the ammonium cation. And let's take a look at this mechanism in a bit more detail, even though you've seen it in your pod. The first step in this mechanism is reaction with your acid. So you want to protonate your carbonyl. This is typically under equilibrium conditions, but I'm going to show one-way arrows because the overall reaction is non-equilibrium. Once we have our protonated carbonyl, that central carbon is really electrophilic. So if you've got water around, this water can easily attack in, pick up electrons. Let me slide this down. What do you think the next step is going to be? Deprotonation. I'm just going to cheat and show this as a proton shift. So plus minus H plus to cut down the number of steps we have to show, and I'm going to move that proton over to the amine. And then just like we're used to seeing, this oxygen can clamp out down, kick off ammonia as a leaving group. And now we're almost there. Once your ammonia is kicked off, that ammonia can steal a proton back to give you your carboxylic acid and ammonium cation. Does that make sense? Pretty similar to the reactions we've been seeing in the past few chapters. The main thing people forget is showing that tetrahedral intermediate. You do need to show that tetrahedral intermediate. It's not an SN2 style reaction. Does that make sense? All right. Base hydrolysis can also occur. So let's say you have an amide. You can accomplish the same transformation using sodium hydroxide, really crank up the heat, and then in the end you need to reprotonate your carboxylic acid, so you treat it with some sort of weak or relatively strong acid, I should say, and you can get your carboxylic acid to pop out. I'm not going to show the mechanism for this, but it follows the same type of mechanisms that we've seen previously. If you notice for both of these though, for the top one, it requires really high temperatures, and this one requires really high temperatures. That's good for us because otherwise our proteins would denature easily. We don't want our proteins to denature easily. So you really have to push on these if you do want to do substitution reactions with amides. All right, the next one's a little bit different. This is a reduction reaction. And we're really not going to get into the mechanism of this because it is bizarre. If you have an amide, you can treat it with a strong reducing agent like lithium aluminum hydride in excess, followed up with a wash with water or weak acid. And you can actually eliminate off that carbonyl and get your amine out. So this is also a clever workaround for making amines. Does that make sense? All right, luckily that's it for the amide chapter. So let's make our super short flowchart or reaction map. Like I said, the best way to make amides is from acid halide, so I'll put that on the far left-hand side. We'll put the amide in the middle. Put a carboxylic acid over here. And I'm going to put a nitrile down there, and I'll talk more about that in a second. So for the first one, you can convert to an amide using ammonia in excess. You can convert to a carboxylic acid two different ways. The first one was just acid and heat. Second one was sodium hydroxide, heat, and then an acid workup. Either one works for hydrolyzing amides. And then for converting to an amide to an amine, you can do this using lithium aluminum hydride. Let me move this down. In excess, followed by an aqueous workup. Actually, I'll just show this as H2O. All right, the bottom one's a little bit tricky, and we kind of skipped over this one, but I'll go over it next. But does anybody remember the name of this functional group? It's a nitrile or a cyanide functional group. Most people would call these nitriles, though, when they're coming off of something else. Cyanide is typically the anion. And you can convert an amide to a nitrile really easily by using thionyl chloride, so SOCl2. We haven't seen this mechanism yet, but we'll take a look at it in this next section here. Does that make sense?
We already have a lot of reactions going on, so why would you introduce NaOH and acidic workup?
It's just important to remember that with these, you can cleave them using strong acid or strong base. It's not that you have to have one or the other, so I like to show both are feasible routes. Yep. All right, so let's take a look at the nitrile section. That's the last section of this chapter. Just like before, we'll do preparation first and then reactions later. And the first one we've actually seen already, although it's not a super popular reaction, is an SN2 reaction to make nitriles. What I mean by this is you have some sort of alkyl halide, or let's say alkyl tosylate. You can treat this with sodium cyanide. And you can just simply do an SN2 reaction to swap off that leaving group for cyanide, right? Key thing to remember is this must be unhindered. Doesn't work if you've got a tertiary alkyl halide, for example. Does anybody know the main downside of this? Cyanide. You could accidentally kill yourself, so it's not the most popular route for making nitriles. However, it still is done on fairly large scales. You just have to be extra cautious when you're doing this. The second one is from amides. And with amides, the reagent I said you needed to use is thionyl chloride. When you do this, you can interconvert this amide to a nitrile. And then just like with all the other thionyl chloride reactions, you kick off sulfur dioxide gas, and you kick off hydrochloric acid as a byproduct. So let's take a look at this mechanism, because it is very strange. So we start off with our amide. Got our thionyl chloride, which is a really good electrophile. And in this case, the nitrogen can donate electron density up to that oxygen. I'm not going to bother drawing that resonance structure, but you get the idea. The oxygen has a very large amount of partial negative character on it. And because of that, the oxygen actually acts as the nucleophile and can attack the sulfur and kick up electrons to that oxygen. Now we've got this highly charged species. The next step, we're going to kick off a leaving group. I'm just going to eject off one of these chlorides. and the nitrogen still has a positive charge. Because that nitrogen has a positive charge, we need to do a proton transfer. So I'm just going to write minus H plus. Now you've got something that looks a lot like an imine, which we saw previously, right? All right, in the next step, you typically have some sort of base facilitate the next part of kicking off sulfur dioxide. So I'm just going to draw a generic base. It doesn't need to be a very strong one. It's going to grab this proton coming off of your imine, kick this down, kick this over in one big cascading sequence. So now once you've done that, you've got your carbon-nitrogen triple bond. That's one of your products. You've got your sulfur dioxide gas, which bubbles out of solution as stinky. And you kick off HCl as well. Does that make sense? It's a pretty good reaction for converting amides to nitriles. There's just a lot of arrow pushing involved. All right, let's take a look at reactions of nitriles. Those are really the only two ways we know of making nitriles, at least in this textbook. The first one we actually already saw, and this goes back to the pod a while ago. I think it was last week, where we said with acid and heat, you can first convert your nitrile to an amide, and then just like we saw, if you keep on pushing this, oops, got my positive charge, you can go all the way to a carboxylic acid. Conversely, you can accomplish the same transformation using basic conditions with sodium hydroxide and heat, followed by your acidic workup. So that's just a review of the pod that we've already seen. So using standard arrow pushing that we're familiar with. The second reaction, in my opinion, is the more interesting one, and that's the reaction with the Grignard. And I like this reaction too because it makes a lot of intuitive sense. So let's say I've got this Grignard reagent, and I'm going to call this R prime MgX. We know that carbon's really, really nucleophilic. It's going to want to attack the carbon over here. And just like we've seen in the other reactions, we can't violate the octet, so we're going to kick electrons up to the nitrogen. So now we have two R groups attached to that carbon. We have a double bond to the nitrogen, two lone pairs on that nitrogen, which gives it a formal negative charge. All right, in the next step, we need to treat this with acid. So I'm going to treat this with just generic hydronium. This is really quickly going to steal a proton back. And you end up with this intermediate. Does anybody remember what this intermediate is called? The functional group? What's that? Not quite. There's no alkene in it. It's a carbon-nitrogen double bond. Sounds like enamine. Imine. So at this point, we've created our imine. I have had students in the past ask me, for that first step, why doesn't the Grignard reagent continue to attack in? Does anybody have an idea? So for example, why doesn't a second equivalent attack this carbon? So maybe sterics. Any other ideas?
electronegativity?
Yeah, if you tried to attack that carbon a second time, your carbon would be forced to have a 2 negative charge. Not happy having a 2 negative charge. So it just stops there and then forms your imine. It's really nice because you can control the addition and ensure the Grignard only reacts one time. All right, now that we've got our imine, we know we can hydrolyze imines back to a ketone, right? So let's review that mechanism. So acid catalyzed hydrolysis of imines. The first step is to protonate your imine. Now it's very electrophilic. If you have a lot of water around, the water will attack in, kick up electrons to that nitrogen. And then in the next step, I'm just going to cheat like before and show a proton transfer. So plus and minus H+, we're going to move the proton from that water over to the amine. So now the amine is protonated, the alcohol is neutral. And then just like we're used to seeing, this can clamp down, kick off ammonia as a leaving group. And then once your ammonia is kicked off, this can really quickly facilitate the deprotonation, where you end up with, oops, sorry, I switched to an OH. That came out of nowhere. End up with your ketone and your ammonium cation. Does that make sense? So it just follows standard arrow pushing. It just looks kind of crazy when you look at it at first to say, I'm starting out with a nitrile. How do I get to a ketone? Just trust your instincts with that arrow pushing. Yep.
So if we're really trusting our instincts, and then we have, so for example, NH3 deprotonates that OH over there, can't we just simply say minus H+?
Yeah, so for that last step, you could write minus H+, but it's important to remember that the best base available in solution is going to be your amine that you kicked off. So you always end up with your amine salt. So your ammonium salt will be one of the byproducts. That's why I like showing it here. Yep. All right, one more reaction. And then believe it or not, we're done with the chapter. Feels like it's been an eternity, huh? Last one is reduction of nitriles. This is another reaction where the book doesn't even show the mechanism, so I'm not going to bother. You can reduce using lithium aluminum hydride in excess, followed by reaction with water. And just like with amides, you can convert this to an amine. So I'm not going to show the full mechanism for it, but it's the exact same reaction as with amides. Nitriles and amides are kind of like cousins to one another. They do very similar chemistry. Make sense? All right, so let's wrap it up with our reaction map for nitriles. I'll put nitriles in the center. And then I'll put reagents that we can use to make nitriles on the left-hand side, and then the products we can make from them on the other side. Oh. All right, so the first one was our SN2 reaction, where we can just react an alkyl halide with sodium cyanide. Bottom one was with thionyl chloride. That was the one where we kicked off sulfur dioxide gas. And then we saw that we can convert nitriles to carboxylic acids. using two different routes. One was just acid and heat and really just crank on it for a while. You'll go past the amide to the carboxylic acid. And the second one was with strong base, like sodium hydroxide, and heat, crank on it, and then make sure that your carboxylic acid is protonated by quenching it with strong acid at the end. The second one that we saw was we can convert nitriles to ketones. So R prime MgX to get that second carbon group on, followed by a workup with water. And then last but not least, we saw that you can convert all the way to an amide by treating it with strong reducing conditions like lithium aluminum hydride in excess, followed by a water workup. So you can tell the reaction maps get a little bit smaller as we go through the chapter. What you can do, and I like to encourage students to do, is to print off a fill-in-the-blank study guide style worksheet. So for example, this one I've got preparation of carboxylic acids, reactions of carboxylic acids, same with chlorides, anhydrides, esters, amides, nitriles, and so on. There's a lot.
This is one chapter.
This is one chapter. But like I said, a lot of them are kind of similar to one another. So if you understand the acid chloride section in particular, you're in really good shape. So if you are trying to triage your studying, which I never suggest doing, try to triage the acid chloride section. That's the most important one from this chapter. There's also, I believe in the study guide, there's a big reaction map where you can interconnect these. What I found is this reaction map does work, but it gets cluttered really, really quickly. So I prefer to kind of separate them out of their big reaction map into their own little mini maps, and that can be helpful too. So choose whatever works best. All right, what we're gonna do for the remaining time is I've got a bunch of in-class practice problems. So I'll hand these out. These aren't going to be collected. You're welcome to work on these or the pod. I just really want you guys to get used to doing a lot of practice problems from the textbook because it looks easy in class until it's presented in a new way. So really try to dig in with these.